In this video, we're going to begin section 5.1.3 on the definition of the double integral and iterated integrals. So the definition 5.1.2, the double integral of a function f of xy over a rectangle R is written like this, the double integral over R of f of xy dA, and it is the limit as both m and n go to infinity of the Riemann sum that we were looking at in the last couple of videos. The sum from I equals 1 to n of the sum from j equals 1 to m of f of x ij star y ij star, delta x, delta y. And of course, that definition is valid only when this limit exists. So a couple things about the notation. Notice first of all that there's no bounds on the double integrals, right? But the region R is written as a subscript for both integrals. And the differential dA here is the interpretation of delta x, delta y. It represents an infinitesimally small bit of area. A couple of remarks. As we saw in the last video, if f of xy is interpreted as a height either above or below the xy plane at every point xy, then the double integral represents the total exact net volume, right? Net because the volume is signed, because f of x can be plus or minus. So it's the volume under the surface of f over this rectangle R. There's other interpretations, as we've seen in previous videos as well. If f of xy is interpreted as a density of a laminate region, it's a very thin region, R at a point xy, then the double integral represents the total mass of the laminate region R. And lastly, another interpretation is if we're talking probability, if f of xy is the joint probability density function of two random variables x and y at any point xy, then the double integral represents the probability associated to the portion of the sample space that is represented by the rectangle R. So evaluating a limit every time would be a pain, and to say the least, it can be quite challenging, but luckily the next definition and theorem give us a way that we can evaluate exactly double integrals using antiderivatives and integration techniques from our integral calculus course. So let's go and read definition 5.1.3. An iterated integral for a function f of xy over a rectangle AB times CD is written like this. And now you notice that the integral does have bounds, and in particular, those bounds are in a very particular order. C and D are on the inside integral, and they are closest to dy because the C and the D was the y interval. Next, A and B are on the outside integral, and so is dx on the outside because that is the A and B, where the x interval. And so an iterated integral, say that 10 times fast, is interpreted as this. So the integral of AB of, so you've got an integral dx, and what's inside is an integral of c to d of f of x, y, dy, where that tells you that you've got an integral like you would have done in Calculus 2, because here, let's read this bottom sentence here, where the notation means that the inner integral is evaluated first by holding the non-integrating variable as a constant. So you would evaluate this integral the same thing that you would have done in a previous calculus course. You just pretend x is a constant and you integrate it as a single variable integral with respect to y. If you switch the order around, so from integral from c to d of the integral from a to b of f of x, y, dx, dy, notice they have switched just like the integrals have switched. Then the interpretation is the outside integral is from c to d of something dy, and the inner integral now is an integral from a to b of f of x, y, dx. So in this case, you would pretend y is a constant, integrate with respect to x, and then in your second step, integrate with respect to y. We're going to see that in just a second in an example. But before we do, let's read Theorem 5.1.1, which tells us why we want this idea of iterated integrals. So Theorem 5.1.1 is Fubini's theorem. And it says if f of xy is continuous on a rectangle R, which is AB cross CD, then the double integral over R of f of xy dA can be evaluated as, you got it, an iterated integral. So it can be either of them. It's telling you, in fact, let me concentrate on writing them though, it's telling you that these are, in fact, equal. You can choose to do either integral, either order of integration, and you will get the same answer if the function is continuous on your rectangle. Let me make sure I wrote this correctly. From a to b, from c to d, dy dx, and from c to d, from a to b, dx dy. Good. So we're going to see a geometric rationale for why this makes sense a little bit later. For now, let's leave that in this video here, and in the next video we're going to do example 5.1.2, where we'll actually evaluate a double integral using iterated integrals. See you in a bit.